This problem is asking us to find the equations for load, shear, and moment for the given beam. Now, in this class, we're defining these equations by taking section cuts and treating the distance to the location of the section cut as a variable x. It's also possible to define equations through direct integration methods with pure calculus, but that's sort of not in the scope of this example. So essentially what we'll do is begin by identifying well, first we'll find our reactions, and we'll find our points of discontinuity, and then locate where we're going to place our section cuts. Then we'll place section cuts, draw free body diagrams, and calculate the conditions of equilibrium at each section cut location, so for a section on either side of the cut. And those equations of equilibrium will have a variable x, the distance to the cut location in them, and using that variable x we'll be able to then define equations for the three quantities of load, shear, and moment. Actually, we can find our load equations first, but to begin, our first task would be to define our reactions. And here we see we have a fully fixed beam, and that would give us three reactions. Prior to that, let's look at our discontinuities first. We see we have three discontinuities, or four, I suppose, if we count our support. We see that there are discontinuities at locations x is equal to 0 meters. So there's a discontinuity at the support, and here would be our x coordinate. It begins at 0 and goes to the length of the beam, so it's 6 meters long. At location 0 we have a support, and we've defined supports as one of our discontinuities. We have x is equal to 2 meters. We have the location of a transition between a uniformly distributed load, or a UDL, and a linear distributed load, or an LDL. At a change in load, we have at a discrete change in load, so a load that occurs that changes suddenly, we have a discontinuity. So at 2 meters, so at 0 is a support. At 2 meters, we have a sudden change in distributed load. At x equals 4 meters, the end of that linear distributed load, we have another sudden change in distributed load. And at x is equal to 6 meters, we have the end of the beam, but we also have a point load and end of the beam. So at any locations of point loads or point moments, those are also discontinuities where we need to redefine our equations of equilibrium. So, therefore, since we have 4 discontinuities, we have 3 regions between the discontinuities, 0 to 2, 2 to 4, and 4 to 6 meters. We need 3 sets of load, shear, and moment equations. These are for regions of 0 is less than or equal to x is less than 2 meters. 2 meters is less than or equal to x is less than 4 meters. And 4 meters is less than or equal to x is less than or equal to 6 meters. So we need equations for the entire length of the beam in 3 segments between our discontinuities. So let's find reactions. We'll use global equilibrium to find reactions. And we know we can use global equilibrium rather than needing to take section cuts and use properties of a frame analysis, because we only have three reactions, and we have three equations. So this will allow us to directly get the reactions with simply drawing a free body diagram. So we'll draw our beam, and our beam is of length 6 meters. So we have 2, 4, 6 meters. We have a uniformly distributed load over the first 2 meters, followed by a linear distributed load. There is a point load of 15 kilonewtons. There is our linear load. It goes up to a maximum of 8 kilonewtons per meter, and it has 4 kilonewtons per meter over the first part of this beam. Dimensions wise, well, first off, we have a vertical reaction at A. We have RAY. Between our points of change in this beam, we have 2 meter lengths. And at A, we have a moment reaction, so MRA. And we draw that as positive because we don't know its value. And we have, technically, we have a force RAX. Now, this is a beam, so we know that the axial force within the beam is 0, but we'll still complete that equation. Sum of forces in X is equal to 0. That's our first equilibrium condition. And this will give us RAX is equal to 0. So we can find that without much effort or thought. Now, we can also find sum of forces in Y will give us RAY, and sum of moments about a point will give us moment reaction at A. Now let's just go ahead and put in our joint locations here for completeness. This is location A, not B. And this is B over here. Now it's easier for us to find these reactions if we redraw this free body diagram using our resultant forces for the distributed load. So let's redraw that, and we have a vertical force of 15 kilonewtons there. And if we look at a region we'll call region 1 and 2 and 3 here, so let's just give ourselves a little 1, and then we'll have a 2 and 3. So we're going to give ourselves resultant forces for the uniformly distributed load between 0 and 2 meters, a resultant force for the uniform part of the trapezoid load between 2 and 4 meters, and a resultant force for the triangular point or part of that trapezoid load between 2 and 4 meters as well. This means that we'll have a resultant force of FR1, a resultant FR2, and a resultant FR3. And all of those resultants will be at different locations. We'll have a location for the first one, the second one, and the third one. We have a reaction force, of course, RAY, and we have X bar 1, X bar 2, and X bar 3, which are the distances to the centroids of the distributed load shapes for regions 1, 2, and 3. In other words, the location of the point of application of our resultant forces. And we have finally MR at A, our reaction moment at A. At this point, we're ready to go ahead and, well, let's give ourselves one more dimension here, and then we can use this second free body diagram with the resultant forces to draw or to define our vertical reaction and our moment reaction. So let's find resultants and the locations at which they act. So first off, if we look at FR1, that is simply the area under this rectangular load. We have 4 kilonewtons per meter acting over 2 meters length is 8 kilonewtons. And X bar 1 is the distance between 0 and the centroid of that rectangle is simply equal to, is equal to 2 meters divided by 2 is equal to 1 meter. We have FR2. Now that's equal to the rectangular area there. So it's equal to 4 kilonewtons per meter multiplied by the distance over which it's acting, so 2 meters length, is also equal to 8 kilonewtons. And x bar for 2 is the distance from 0 to the centroid of that. So we have 2 meters to the start, so this 2 meters, and then the distance from here to the centroid of that shape is 2 meters over 2, and this gives us 3 meters. And we have FR3 is the area of the triangular portion of that load. So we have the magnitude 8 kilonewtons per meter minus 4 kilonewtons per meter times the distance, 2 meters, all divided by 2. And this magnitude of the resultant force there is simply 4 kilonewtons. And finally, the location of that force is going to be equal to 2 meters plus, so we're going to go over this 2 meters to the start of that triangle, plus the distance to the centroid of that triangle is 2/3 times the length of the triangle itself, and this will give us a distance of 3.333 meters. Now at this point we've got the magnitude of all our resultant forces and their locations. We're ready to find our moment and force resultants. So let's take the sum of moments about location A and set it equal to 0. And this will give us MRA, our reaction moment, and we've defined that as acting positive, or we've assumed it's acting positive, so we drew it that way, minus FR1 times X bar 1. And this is a moment, this force trying to rotate about this location is trying to rotate it clockwise, which we've defined as negative, minus FR2, also trying to rotate it clockwise, so FR2 times X bar 2, minus FR3 times X bar 3, also trying to go clockwise. All of these are negative moments. And then finally minus our 15 kilonewtons times 6 meters, also trying to go clockwise, and all of that is equal to 0. Now we can plug in the values that we know and solve for MRA. So let's move all the force resultants in that 15 over to the other side of the equation. We have MRA is equal to, and if we plug in our values, 8 times 1, so that's FR1 times X bar 1, plus, it's plus now since we move it over to the other side, plus 8 times 3, FR2 times X bar 2, plus, once again because we moved it to the other side of the equation, 4 times 3.333, and then plus 15 times 6 is equal to 0. Oh, not equal to 0. We already accounted for that when we moved all these components to the other side. So reaction moment at A is equal to the sum of all the other moments. And then we can add everything up, and we see that we have 135.333 kilonewton meters, and we found it was a positive value. So the reaction moment at A is 135.33 kilonewton meters. And the only thing that's left unknown to us is the reaction force at A. So we can take sum of forces in Y and set that equal to 0. If we add up all the forces in Y, we see we have a positive RAY minus FR1 minus FR2 minus FR3 minus 15 is equal to 0. Now if we move all of these forces to the other side to solve for RAY and plug in values, we get RAY is equal to 8 plus 8 plus 4 plus 15. And RAY is equal to plus 35 kilonewtons, which is acting up. So now we know our reaction moment and forces, and we're ready to begin solving for our shear and moment equations over the different regions of the beam. And we said that we're going to find them for 0 to 2, 2 to 4, and 4 to 6 meters. So to do that, we're going to need to place section cuts through our beam itself. And these section cuts will occur at locations in the regions between the boundaries that are established by discontinuities. So between 0 and 2, we need to place a section cut. And let's use green for this. We'll put a section cut at a location AA. And we'll also need a section cut between 2 and 4 meters. So this will be at location B. And finally, we'll need one between 4 and 6 meters. And we'll note that we don't put a dimension to that section cut anywhere. The section cut itself is at an arbitrary location between the two boundaries of that region. So let's begin with determining the equations for region 0 to 2 meters. And to do that, we will cut through location AA. Now, we know that AA is defined as being in region 0 is less than or equal to x is less than 2 meters. So we're working only within the bounds of 0 to 2 meters. In other words, the equations that we define will only be valid over those regions. Now let's draw a free body diagram of one side of the beam. I would argue that the side to the left of AA would be the simpler side for us to analyze. So we'll go ahead and draw the free body diagram of the left-hand side of the beam. And this beam will have a UDL acting on the beam itself, and we will be loading with W of x, and we can say that W of x is equal to a constant of 4 kilonewtons per meter over that length. So we were asked to define the equations for load as well. Now the load is uniformly distributed constant. So simply the load as a function of x is equal to 4. We know we have a reaction moment that we solve for. This MRA is equal to 135.333 kilonewton meters. We have a vertical reaction force that we solved, and this is RAY is equal to 35 kilonewtons. We have a resultant force that we could draw. Let's just draw it on this diagram. So the distributed load itself would create a force resultant, FR1. And that force resultant would occur at a location that we'll call X bar. Now we made a cut at a location over here, and that location, the distance between 0 and that location, is defined as x, our variable. So this is the cut location of A, where we cut this beam. At a cut in the beam, we expose the internal shear force on this beam, shear as a function of x. And we draw this according to our positive sign convention for local shear, which is acting down on this face of the cut. And we have a moment that we exposed. Moment as a function of x, and we draw it as according to our positive sign convention for drawing moment in our local coordinate system where we cut, and this is a moment that is rotating counterclockwise on this side of the cut, and it would be clockwise on the other side of the cut. Or it would sort of be cupping the top of the beam. It would be trying to rotate the top of the beam and to make it sort of hold water, we sometimes say. Either way, this would be our positive sign convention for our unknown member forces. And they represent absolutely everything that's happening on the side of the free body diagram that we didn't draw. So the remainder of the beam. So to solve this problem, we first need to identify the magnitude of FR1, and that's simply equal to the magnitude of load times the length over which it's applied, since it's a rectangular load. So we'll say that that's equal to the length, x, multiplied by the magnitude. So the resultant force is equal to 4x. And x bar, the centroid of that area, is simply equal to x over 2. Half the length of that beam segment. Now, at this point, we're ready to put this in equilibrium. So we'll apply equilibrium equations. And these are simple to apply. We can apply the sum of forces in y is equal to 0. And this will give us, if we add up all the y forces, we have our force resultant acting downwards, we have our RAY acting up, and we have our shear acting down. So RAY minus FR1 minus shear as a function of x is equal to 0. Now if we plug in our values that we know and solve for shear, we can get shear as a function of x is equal to negative 4x plus 35. So the 35 is the value of RAY, and the minus 4x is the value of FR1. And we note that that this is, well, it's we don't know. The reason it's negative here is we moved FR1, well, we moved shear over to this side and it became positive, and FR1 stayed negative and RAY stayed positive. So we solved for the equation of shear that's valid between 0 and 2 meters. And now we'll go ahead and solve for the equation for moment over that region. So we can take the sum of moments about location AA and set that equal to 0. So we'll take the sum of moments about this point. And this will give us our reaction moment, which is positive, plus our moment as a function of x, which we drew in counterclockwise direction, positive according to our local sign convention, plus FR1 times x minus x bar. So it is the moment of this force, which would be the magnitude of the force multiplied by the distance away, which is x minus x bar. Minus RAY times x. And that's negative because it's trying to rotate it counterclockwise or clockwise direction. And all of that is equal to 0. If we rearrange and solve for moment as a function of x, and then we can see that we have moment of x is equal to RAY x minus FR1 x minus x bar minus MRA. Now we know some values here, so we'll start to plug them in. Moment as a function of x is equal to 35 x RAY times x minus 4 times x times x minus x over 2. So FR1 is 4x, we've defined that here, times x minus x over 2, which is x minus x bar, minus MRA, which, well, we can plug in the value for that. So this will be minus 135.333 kilonewton meters. Now if we multiply this out and simplify, collect like terms, we can solve for moment as a function of x is equal to negative 2x squared plus 35x minus 135.333 kilonewton meters. So that gives us the equation for moment acting over the region 0 to 2 meters. So here we would say 0 is less than or equal to x is less than 2 meters, and the same for here. 0 is less than or equal to x is less than 2 meters. And the same for here. 0 is less than or equal to x is less than 2 meters. Okay. So we've solved for one of the regions, the region between 0 and 2 meters, and we found the equations for load, shear, and moment by taking the section cut and treating the distance to that cut as a variable. Now let's take a cut at BB. So we'll cut through the second region between discontinuities, the region of our linear distributed load. So BB is in region 2 is less than x is less than 4 meters. And we're going to need to define or draw our free body diagram and also define our equation for load over that region. So if we cut through location BB here, we can see we'll have the possibility of drawing the free body diagram on the right hand side of the beam or on the left hand side of the beam, and they're both arguably about as difficult for us to calculate. So let's stick with the left hand side, but there's no real reason why we chose to stay there. It's just the choice of the person doing the problem. So we have our beam itself. At a location at A. I suppose I should go up here and label our joint A there. So at location A, we have MRA is equal to 135.333 kilonewton meters. We have a reaction force RAY is equal to 35 kilonewtons. Over a length of 2 meters, we have a uniformly distributed load of 4 kilonewtons per meter. Now between 2 and the location of our cut, we have a linear distributed load with a equation W of x. And that occurs over a distance. If we look at the distance to our cut, as being x. The distance between here and here is x minus 2 meters, since that's 2 meters there. This is our cut location itself. This is B. At B we have a shear of x, and we have a moment as a function of x, and that's drawn according to our positive local sign convention. Now let's find W of x, our equation for load over that region. And we can say that it's a line, it's a linear line, or a linear load, so it's going to be of the shape W of x is equal to mx plus b, where m is the slope and b is our y-intercept at x equals to 0. So m is equal to w2 minus w1 over x2 minus x1. And let's go here and let's look at what our load really looks like. So between the region of (2 meters and 4 meters, between this point and this point, we have a load that goes from 4 kilonewtons per meter all the way up to 8 kilonewtons per meter. And this is what we're defining as W of x. Our load is a function of x. And if we were to extend that out, we could see that at x equals to 0, we could see that our intercept would be equal to 0. So at location x equals 0, W of x equals 0. And we can look at similar triangles to get that. We could take the triangle here, which would be of a magnitude 8 minus 4. So 4 over 2 is proportional to 8 over 4. And it's pretty easy to see that B, our y-intercept at 0, would be equal to 0. And let's look at our slope itself, the slope of this curve. So if we take W2 is equal to 8, and W1 is equal to 4, and divided by x2 is equal to 4, and x1 is equal to 2, so the coordinates of this point and this point, we would see that we have 2 kilonewtons per meter squared is the slope of that line. So this will give us an equation for W that we can write down here. W of x is equal to 2x. So mx plus b, and b is 0. M is 2, x is our variable. So we've defined the equation for load over that region. W of x is equal to 2, and this is valid for 2 is less than or equal to x is less than 4 meters. So now that we have the load, we're going to have to go through and find the values for shear and for moment in those regions. And to do that, let's redraw our free body diagram, but now we'll place resultant forces in there instead of the distributed loads. Now if we do this, we would see that we'd have our beam, our beam itself. We have this moment at A, we have a reaction force, RAY is equal to 35 kilonewtons. Let's draw on our distributed load, and then we'll draw our resultant forces on top of that. So we have our distributed loads over the length of this beam of 4 kilonewtons per meter and of W of x is equal to 2x that we just solved. And we'll define some distances. We have a distance between 0 and our change in load of 2 meters. We have x minus 2 that we've already defined. Our resultant forces, the region between 0 and 2 puts a resultant force FR1 on the beam. The region between 2 and 4 meter, or 2 and the cut, I should say, puts a resultant force FR2 and a resultant force FR3. And FR2 and 3 and 1 correspond to regions of, this is region 1, this is region 2, and this is region 3. So we can look back at how we solve for the reactions, and we're just mirroring that that description for how we're defining FR1, FR2, and FR3. And they each will have a x bar associated with them, a distance to their neutral axis, x bar 2, and x bar 3. And finally we'll have a entire dimension here of x. The last thing that we're missing here is our shear and moment at the cut. We have a shear of x and a moment of x, both drawn according to our positive sign convention. So let's find the magnitudes and locations of our resultant forces. We can say that FR1 is equal to 2 meters times 4 kilonewtons per meter is equal to 8 kilonewtons. And x bar 1 is equal to 2 meters over 2 is equal to 1 meter. And then we have the second resultant force. FR2 is equal to the area under this rectangle, so it's going to be x minus 2 times the magnitude of the force times 4 kilonewtons per meter. And that will be equal to FR2 is equal to 4x minus 8. So let's just start underlining a couple things so we can go back to them pretty quickly here. And we'd say that this one is equal to FR1, this is equal to x bar 1. Now x bar 2 is equal to the distance from zero to the location of that centroid, so it'll be equal to 2 meters plus x minus 2 over 2. And that will be equal to x over 2 plus 1 is equal to x bar 2. So we have the distance to the second point load application. And finally, our third resultant force would be the resultant of the triangular load there. So the magnitude of that, FR3, will be equal to the magnitude of the load at that value of x. So it will be equal to W of x, which is the magnitude here, minus 4. So that's the magnitude of the height of that triangle. Multiplied by the length of the triangle is x minus 2, and all of that divided by 2. And we can rewrite that by plugging in some values. So W of x is 2x minus 4 times x minus 2. And all of that's divided by 2, and we can end up rewriting FR3 is equal to x squared, let me just restart that, x squared minus 4x plus 4. So that was a relatively tricky one, but really it's just the height of this section of the triangle, which is W of x minus the value between 0 and here, so minus the rectangular portion of it, which is 4, so W of x minus 4, times the length divided by 2. Now x bar 2 is not that, or x bar 3 is not that difficult to find. We have x bar 3 is equal to 2 meters, so this value, plus x minus 2 times 2/3. And if we rewrite that, just expand it and collect like terms, we could see that x bar 3 is equal to 2x over 3 plus 2 over 3. Wonderful. So now let's redraw this diagram once again down to its simplest state, the bare minimum information that we need in order to solve the shear and moment equations. We'll draw the beam itself. We will apply the external reaction force of 35 kilonewtons. This is RAY. We'll apply the reaction moment. MRA is equal to 135.333. We'll apply the FR1 is equal to 8. And FR2 is equal to 4x minus 8. And FR3 is equal to x squared minus 4x plus 4. So let's just divide this from the rest of the problem here, so it becomes a little bit more clear. We have our shear, and we have our moment, and then we have our distances. One meter, x over 2 plus 1, and two-thirds x plus 2/3, and finally x itself. So at this point we could apply equilibrium. And by applying equilibrium, we'll be able to solve for the values of shear and moment as functions of x. So we'll start with the sum of forces in y is equal to 0. And we'll add up all the terms in the y direction. So we have RAY, this value acting up, minus FR1, that value acting down, minus FR2 acting down minus FR3 acting down minus shear as a function of x, all acting down. So adding up all the vertical forces on this diagram. Now we'll solve for shear and plug in values. We get shear as a function of x is equal to 35 minus 8 FR1 minus 4x minus 8 FR2, and finally minus FR3 x squared minus 4x plus 4. Now if we simplify this, we can write shear as a function of x is equal to 31 minus x squared. And that's valid for a region of 2 is less than x is less than or equal to, or sorry, we're going the other way. 2 is less than or equal to x is less than 4 meters. Now we can take the sum of moments about the cut location, which is about location B, and set that equal to 0. And this will allow us to solve for moment as a function of x. If we start to plug in values for that, we'd see m of x going positive, this value here. We're taking moments about the cut location there. So m of x plus mRa, which is also going counterclockwise, plus fr1 times x bar 1, x minus x bar 1. So this whole distance minus this distance is the moment arm for FR1 plus FR2 times x minus x bar 2 plus FR3 onto x minus x bar 3 minus RAY onto x itself is equal to 0. So we have a fair bit going on in this particular moment equation. So we can start to plug in our values here, and we'd see moment as a function of x plus MRA is 135.333 plus FR1 times x minus x bar is going to be 8 onto x minus 1 plus FR2 is 4x minus 8 onto x minus x bar 2 is x minus x over 2 plus 1 plus FR3 times x minus x bar 3, which would be x squared minus 4x plus 4 onto x minus 2x over 3 plus 2 over 3, and finally minus RAY, which is 35 onto x itself. All of that is equal to 0. If we now multiply out our terms, we would see we'd have moment as a function of x plus 135.333 plus 8x minus 8 plus 2x squared minus 8x plus 8 plus x cubed over 3 minus 6x squared by 3 plus 12x by 3 minus 8 over 3 minus 35x, and all of that's equal to 0. Now we can collect like terms, and we see moment of x plus x cubed over 3 minus 93x over 3 plus 398 over 3 is equal to 0. And if we solve for moment as a function of x, we'd get moment of x is equal to minus 1 over 3 times x cubed minus 93x plus 398. And at that point, we've solved for moment and for shear and for load as a function of x for the second region, which is 2 is less than or equal to x is less than 4 meters. And we'll note that that was very time consuming and a fair bit of algebra involved, but really the concept was not too difficult. The problems came from us having this linear distributed load, and the linear distributed load resulted in a cubic equation for moment and a quadratic for shear, which was a little time consuming to solve, but it wasn't too bad. So our last step would be to cut in the final location, location CC. We're going to want to cut through the remaining portion of the beam. So we'll cut through CC. And when we do this, we can draw our free body diagram, and we can draw the free body diagram for either side of the cut and place it in equilibrium. In this case, it is far simpler for us to analyze the right-hand side of this cut than it is the left-hand side, where we have the reaction, the uniformly distributed load, and the linear distributed load. Whereas on the right-hand side, we have a single point source of load. So let's draw the free body diagram for the right-hand side of this beam. And we'll cut the beam itself. We'll apply the point load at the end of the beam of 15 kilonewtons. And that end is end B. And we'll note that our distributed load function, W of x, is equal to 0. There's no distributed load on the beam, therefore we have no load function. We do have a single point load, but that's at the boundary of our region. That's our discontinuity itself. So W of x is equal to 0 from the region of 4 is less than or equal to x is less than or equal to 6 meters. Let's start to put some dimensions on here, I suppose. We have a distance between the location of our cut. Our cut was at this point here, B, or sorry, we're at C now, CC. So at CC, at this location, we're at the entire distance is 6 meters, and here the distance between 0 and the cut is x. So the distance between the cut and the end itself will simply be 6 meters minus x. And we have our internal shear, and in this case the shear force is acting upwards, because that's a positive local sign convention for this side of the cut, and our moment is acting clockwise. Those are both drawn as positive shears and moments. And that's the entire free body diagram. It's really going to be quite simple for us to solve. Let's do that. Let's apply equilibrium, and we have sum of forces in y is equal to 0. Adding up everything in y, we get shear as a function of x acting up. Minus 15 is equal to 0. This gives us shear as a function of x is equal to 15 kilonewtons. Which, sorry about that, let me try and adjust this. Okay, so shear as a function of x is equal to 15 kilonewtons, which is valid for a region of 4, which is less than or equal to x, is less than or equal to 6 meters. And we can put a box around that one because that's part of our solution. And if we take the sum of moments about location CC and set that equal to 0, we can see we have minus moment as a function of x. It's minus because it's going clockwise. Minus 15 times 6 minus x, and it's negative because it's going clockwise, is equal to 0. And if we plug in some, or if we expand this and collect terms, we'd see we'd have minus moment as a function of x minus 90 plus 15x is equal to 0. And solving for moment as a function of x, we get 15x minus 90. And that's valid over the same region. 4 is less than or equal to x is less than or equal to 6 meters. So this particular portion of the beam was the simplest for us to solve because the distributed load was 0. And a 0 distributed load resulted in linear shear, or constant shear and linear moment. Pardon me. So let's give ourselves a little summary table of the equations. Now we're going to have a region, an equation for load, an equation for shear, and an equation for moment. So our regions were defined as the locations between discontinuities. So we had 0 was less than or equal to x was less than 2, and 2 was less than or equal to x was less than 4, and 4 was less than or equal to x was less than or equal to 6. Load was defined as a constant over that region. First region, linear over the second region, and 0 over the third region. Shear was linear over the first region, was a quadratic over the second region, and was constant over the third region. Moment was quadratic in the first region, it was cubic. That's a negative. Let me just let me fix that if I can here. It was cubic minus 1/3 times x cubed minus 93x plus 398, and it was linear in the final region. Oh, that's a minus. Minus 90. So we've defined our equations over those regions, and let's just let's plug in some points to that. So let's make another table here where we have x in meters, and shear in kilonewtons, and moment in kilonewton meters. And if we plug in their values for 0, 2 meters to the left of the, just to the left of 2 meters, so in other words, working in region 1, and 2 meters to the right, and 3 meters, 4 meters. Oh, I missed a 1. I'm doing pretty poor here. So let's get rid of that and start this table. Again, sorry about that. So instead of 2 meters, we're going to go down to 1 meter. We'll just go in 1 meter increments. 2 meters to the left, 2 meters to the right, 3 meters, 4 meters to the left, 4 meters to the right, 5 meters, and 6 meters. And then if we plug in our values of shear, we would get 35. So 35 minus 4 times 0 is 35. We would get 31. 35 minus 4 times 1 is 31. 2 meters to the left, 35 minus 4 times 2 would give us 27. And if we work at 2 meters to the right, we'd be 31 minus 2 squared would also give us 27. Using that same equation, we'd get 22. And then at 4 meters to the left, we'd have 31 minus 16 would give us 15. On the other side, at 4 meters to the right, we have a constant shear of 15, 15, and 15. Using the same ideas, we'll plug in the values into our moment equation as we progress down. We have minus 135.333, minus 102.333, minus 73.333, minus 48.667, minus 30, minus 30. Oh, am I missing? Oh, I missed a value for 73 here. So let's get rid of this 48 and 30. All right. So at 2 meters to the right, we're at 73.333 as well. At 3 meters, we are at minus 48.667. And then we have our minus 30, minus 30, minus 15, and 0. Okay, so at this point, we're finally ready to begin plotting these curves. And that is not too bad for us to do, because we know a little bit of how curves should look, and also we have the equations and the values for them themselves. So if we come to our shear diagram first, and go to region 0, x equals 0, we'd have a value of 35. And that would be here, plus 35. Then we could plug in 31 and 27 as well. And we know that this equation is linear. So it's linear in the first region. And it has an equation of shear as a function of x is equal to 35 minus 4x. And in the second region, we're dealing with 31 minus x squared. So in this case, we're quadratic. So we start at 27, and then 22 and 15. So there's 27, there's 22 and 15 over here. And it's not linear, it's quadratic, but it's not curving very rapidly. And then finally, in the last region, we have a constant shear. Shear of x is equal to 15. We'll note that we begin at 35, and RAY is 35. We end at 15, and then we have this force to push us back down to 0. So everything works out for shear. Now for moment is negative over the entire length of the beam. It starts at a value of minus 135.33. And that happens to be equal to the value of moment at the support as well. And we can plug in some other values here. So this is a quadratic moment equation. But we see that we have a moment of minus 102 and a moment of minus 73.333. And we're quadratic. There. That's not a very good drawing, but it's a very gradually sloping curve. And we have moment as a function of x is equal to minus 2x squared plus 35x minus 135.333. So it's curving downwards. It's a negative parabola. The curvature for it is acting downwards. In our region between 2 meters and 4 meters, we have a cubic relationship for moment. And we start at minus 73.333. We go to 48, minus 48.667, and minus 30. And this is cubic. And we have moment as a function of x is equal to minus 1/3 times x cubed minus 93x plus 398. And then finally, in our last region, we have a linear moment distribution. It goes to minus 15 and then to 0 at the end. And we have moment as a function of x is equal to 15x minus 90. And we'd see that here we have linear, and here we have cubic. So at that point, we've completed the problem, and we've solved for the moment and shear and load equations for the entire beam by taking section cuts and keeping x as a variable the entire time.